All right, so last time we were taking a look at designing filters. In particular, special kind of filters we refer to as convolutional filters. Okay. So very briefly, we looked at the idea of the convolution, and a couple of the concepts, especially if you're not from engineering background, that you should remember is that if we have any kind of system, any kind of linear system, so all linear systems in nature behave like this. If we give it some input x of t and there's some output y of t, the relationship between y of t and x of t is based on the convolution. So y of t is convolution of x of t. Convolution sometimes we represent with the x with a circle in it. So it's a convolution of x of t with h of t. What is h of t? H of t is referred to as the impulse response of the system. Okay, meaning if for the same system, if we give it an input of delta t, whatever output it produces, we call it h of t. Okay, what is delta of t? Delta of t is basically something with infinite magnitude at time 0. So if this is the time. And the properties of the delta of t is if we integrate, we'll get 1. Okay. So the area under this impulse, which is basically very extremely small width and a very high amplitude, such that the area is 1. Typically, we'll draw it like, as a magnitude of 1. Okay. The other property of the convolution is that if we do, other property of the impulse is if we do convolution of impulse with any function. So for example, you're given f of t, you do a convolution with delta of t, okay, you'll get f of t back. So it doesn't do anything, okay? So even though we represent convolution like this, as we discussed in the last lecture, the actual integral is minus infinity to infinity. We change the time scale to some tau scale, then we write it like this. Alternatively, rather than flipping the impulse response and sliding it over, we can also do minus infinity to infinity x of t minus tau h tau d tau. Okay. For your purposes, like I said, you don't have to worry about evaluating the integrals if you can just understand what's the intuitive idea behind it. The intuitive idea, as we went through a simple example last time, was if you are given some signal x of t, if you are given some other signal h of t, okay, let's say 4, 5, 6, 0, 1, 2, right? So what is convolution doing? For example, if you focus on this part, okay, x of minus tau basically is flipping this thing. So if we change this t scale to tau scale, so this is what x of minus tau will do, right? And then t minus tau is basically a slide. So t minus tau is basically, so this is t, this will be t minus 1, this is t minus 2. So this is how x of t minus tau will appear, right? And then all we are doing is multiplying 2 and integrating. So as we discussed, as we flip it and start to slide over here, okay, as we keep sliding and multiplying, when t becomes 4, There's no overlap over there, so the integration will produce 0. As we start to slide further, now there will be some area under the curve. So essentially what the convolution will produce is something from 4 to 8. It will produce some output like this. The maximum will be when t is reaches 6, because at that point you can see there will be maximum overlap between the two signals. So for your purposes, like I said, especially if you're coming from a computer science background, if you can remember one simple concept, what is convolution? It's basically flip, slide, and integrate. Okay, flip one signal, start sliding it, and then start integrating it, right? Okay, what does it tell us? What's the purpose of it? It basically tells us when two signals are overlapping or have more in common. So intuitively, that's the idea behind convolution, okay? But as you will see, there's another purpose of convolution, which is basically not only just to tell us where the overlap is, but also enhance one of the images that we will do convolution on in a certain way, okay? But there are a couple of concepts that we will be using from convolution, okay? So from your point of view, so this was important. The other important part was convolution in time domain equal to multiplication in frequency domain, and vice versa. Okay, and vice versa, meaning multiplication in, convolution in time domain, meaning multiplication in time domain will become convolution in the frequency domain, okay? So, vice versa. Okay, so now let me show you how we will use this concept to design filters that we will apply to images to enhance them in a certain way, okay? So one of the things that we often do is, so we'll take a look at the first filter, will be to, the goal of this filter will be to remove noise. Okay, so noise removal. Okay, so let me sidetrack a little bit and show you the intuitive idea, then we'll come back and see how we will build this convolution filter. Okay, so let's say we're taking a look at stock market data. So maybe IBM or something, right? So if this is days or date, you know, could be date on the x-axis, the price on the y-axis, right? So every day, for example, if we take a look at price of IBM, it's changing. Okay? So it might go up, down, up, down, up, down, up, down. Okay. So this is how it will look, for example, on a daily basis. People who deal with stock market often are interested in buying the stock at a low price and then selling it. So for example, ideally what you would like to do is you'd like to buy it at this point, so and sell it at this point. Okay. So what we try to do is we try to see which way is the stock going. For example, if it's on the upward trend, so if it's on the upward trend, you'll buy. If it is on the downward trend, you'll sell. Okay. But the problem is, see, on a daily basis, there are too many fluctuations. So for example, if you were here, right, the next day the price went down, so what would you do? You'll sell it, you will not buy it, right? So what we want to do is we want to remove the noise from it. Easy way to remove noise. Okay, so one way. To remove noise is by a low pass filter. Meaning pass our data through what we call a low pass filter. Okay. If we take a look at the behavior of a low pass filter in the frequency domain, if this is the frequency, okay, the low pass filter, suppose this is called H of F, that's the impulse response of the filter in the frequency domain. It will look something like this. Okay, there will be some cutoff frequency. Okay, for example, let's forget images for a minute. What if we were designing a filter to remove audio noise that occurs maybe at above, let's say, 12 kilohertz? Okay, so in that case, what you will do is you'll create a filter with a 12 kilohertz filter. So what that means is if there's any frequency above 12, let's say this is 15 kilohertz, as we pass it through the low pass filter, okay, let's say this was 1 volt minus 1 volt, so we feed it to our low pass filter, what will happen? It will zero it out, it will make it basically zero, very close to zero. Okay, in the practical world, it will not be exactly zero, but it will be very small magnitude. But let's say there's some frequency over here, let's say it's 6 kilohertz instead of 15. So if we pass it through over here, what will happen to it? As you can see on the output, if it is 6, it appears without any change. So on the output also will appear, slightly delayed, but it will still be a good magnitude. So in short, a low pass filter will pass all the low frequencies. So low pass filter. It will pass all these low frequencies, and above a certain cutoff, it will suppress all the high frequencies. So that's how the filter works, right? So now coming back to our stock market example, one way to remove the noise, like I was saying, is first, let's pass it through a low pass filter. Okay, a very easy way to create a low pass filter is, so one easy way to create a low pass filter is to use what is called moving average technique. Okay, so in a moving average, what we do is we pick a window size. For example, we may say average the price over the last 5 days. Okay, so if we take a look at the IBM price as an example, okay, let's say day 1, okay, let's say day 1 the price is 120.5. Day 2 price is 121.7. 3, 119.3, 4, 129.4, 5, 120.7. So you can see every day it's going slightly up, slightly down, right? If we were creating a moving average filter, and our window size is 5 days, what we'll do is we'll take the data for the 5 days and take the average, and then that will be our first output. So on the day 6, our data that will produce will be the average of this data. Okay, same way, so this is day 6. Day 7 will be again, so suppose on day 6 the price was 123.1. Okay, so now we will take the average of the next 5 days. So that's what we mean by a moving average. Take the average of the 5 days, then next 5 days, then next 5 days, and start plotting them. Okay, once we do that, what you will see is it will filter out all the daily changes. It will make this curve more smooth like this. Okay, now it's very easy to compute the derivative, take the slope, or compute the slope and see is it going upward or is it going downward. So we can create a moving average for the 5 days, for the 7 days, for the 3 days, for 20 days. You decide what that moving average will be. Okay, so to summarize what I'm trying to say is if you're given some data, especially if it's a one-dimensional data, actually it doesn't matter whether it's one-dimensional, two-dimensional, but for a one-dimensional, easy way to create a filter is just start taking the average of the last 5 or 6 days, then keep moving it, keep moving that average, keep moving that window, and it will filter out all the fast changes, right? Okay, so coming to our images now. Clean this up a little bit. Okay, so if we wanted to create a moving average equivalent type of convolution filter. Okay, so now let's say we have image data. And to make it easier for us to understand, let's convert it to grayscale. So we talked about the formula for converting RGB to grayscale. And let's say the pixel values are 91, 112, 87, 120, and so on. 83, 70, 40, 90, 110, 91, 82, 65, 33, and 70, and so on. Let me pick one more set of numbers. 120, 60, 90, 40, and so on. Okay, so anyway, let's pretend this is some image. This is the data. Okay, so just like in the signals world, if we have a time signal, we can do a moving average. Okay, our images are essentially two-dimensional data. Okay, so here what we do is instead of doing a convolution in terms of the integrals, we do what is called a discrete convolution. Okay, so first, so remember we talked about in the continuous time domain. Okay, our y of t was related to x of t convolution h of t, which is minus infinity to infinity x of tau, h of t minus tau, right, d tau. Okay, so same way in the discrete world, if we are given a signal like this, for example, what we do is we sample it. So every 1 second or every 2 seconds or 2 milliseconds, we'll find out what's the value of it. So what's the value of it? What's the value of it? Okay, suppose the value of this particular signal is 0.7, 0.8, then let's say 0.65, and so on, right? Okay, so we can represent this particular signal as a sequence of sample numbers. For example, 0.7, 0.8, 0.65, and so on. So this is basically our discrete sequence of numbers. Okay, so again, let's pretend we wanted to give you the same example as we did before. Here's one signal, here's another signal, right? And we wanted, now both of them are in the discrete domain, meaning we sampled them. Okay, or let me make it the same as this one. Okay, so let's pretend, sorry, I have two values here, two values over here. Okay, so pretend as I take a look at each sample, what's the value of it? So this will be represented by 1, 2, 3, 4, 5, 6, 7 numbers, as you can see, right? Or let me make it easier to follow. Let me reduce the numbers. Okay, so let me just represent the signal by 5 numbers. Okay, so what are those numbers? 0. Let's pretend this is 0.5 because the maximum was 1. Then 1, 0.5, 0. So this is my, see previously we were calling this in the continuous domain, we were calling it x of t. Now we will call it x of n. And n could be 0, n could be 1. So if n is 2 as an example, what will be the value of this signal? 1. If n is 3, it will be 0.5, right? Same way over here, this was our previously it was h of t. Let's call it h of 1. So again, let's pretend we have 5 values over here. Okay, so anyway, you'll see the sequence will be something like 0, 0, 0, something. 1, 1, 1, 1, then 0, 0, 0. So this will be our h of n, right? So very similar to how we discussed, we flip one signal, we slide it, right? Same thing we'll do over here, we'll flip it. So then this will become, yeah, I should have picked, okay. Let me pick a slightly different example. Let's say one signal is 1, 2, 3. I'll pick an easy example. The other signal is 0, 4, 5, 6. Okay, so this is, let's say, x of n. This is h of n, right? If I do the convolution, then what will happen is, see if I draw it, this will be 1, 2, 3, right? Let me make it easier. Let me just make it 4, 5, 6 for right now. So if you take a look at this signal, this is, or let's make it 4, 5, 2. So this is 4. This is 5. And this is 2. Okay, let's pretend this is h of n. Okay, and this is x of n. So once again, what do? We flip it, we slide it, and then the integration becomes summation in the discrete world. Okay, so if I flip it, what will happen? This will become 1, 2, 3, right? And then I start sliding it. So once, as you can see, this reaches this part over here, 1 will be multiplied by, what was the value over here? 4. So it will be 1 times 4. Everything else is 0. So the first value will produce will be 4. Then once this has reached, so this is the 1. So I'm just putting the slided version in the green color. Then this is 2. And then this is 3. Right? So now you can see, so the first value it produced was 4. So the second value will produce will be 4 times 2, 8, plus 1 times 5, 13. Okay, and same way if I slide it one more, so is it 20? 24. 24, okay. Okay, if I further slide it one more, then you can see 3 will appear in the position of 5, and 2 will appear in the position of 2.
19.
So 3 times 5 plus 2 times 2. 19, right? Then if I further slide it, this 3 will appear over here. So 3 times 2, 6, and then it will go back to 0. So this is how the 4, 13, 19, 6, 0 will be the result of the discrete convolution. Okay, so now let's extend this idea to images. So let's say this is given to us, some kind of image with these grayscale pixel values. Okay, and what we wanted to do is we wanted to apply a convolution. Now we'll be doing two-dimensional convolution, okay, in the discrete domain. So typically what happens is, so somebody will give us a convolution, just like we have h of n over here. Okay, the equivalent of h of n, now this being previously was 4, 5, and 2, right? 4, 5, and 2. Now it will be like a 2D array or a matrix. Okay, so we refer to this as a convolution kernel. Okay, so our convolution kernel, let me just pick one example. 1, 2, 3, 0, 1, 1. 1, minus 1, 0. Let's pretend somebody gave us this 3x3 convolution kernel. Okay, your goal is now to do a discrete convolution of the image with this kernel. So this needs to be done a convolution with the image. Okay, so how will we do this? Okay, so remember in convolution you have to flip one signal. Okay, so just like this was the original, I flipped it, right? In a 2D, again, either, and it doesn't matter which one you flip. Either you flip this one or you flip this one. Okay, so the question is, what is flipping in 2 dimensionals? Okay, the flipping in 2 dimensions, so flipping in 2D is rotation by 180 degrees. Okay, so let me show you how that will work. Okay, so it's easier to rotate the kernel than rotate this big image, but the answer will come out to be the same, doesn't matter what we do. Okay, so first let me show you how do we rotate by 180 degrees. So think of this, easy way to do this is rotate by 90, then rotate again by 90. Okay, so if I rotate this kernel by 90 degrees, what happens is the row becomes a column. So this 1, 2, 3 will move over here. See, this was a row over here, then it will become the column. Okay, then this 3, 1, 0 was previously the column. So then what will happen to it? This column will become a row, 3, 1, 0. So just go on the outer boundary and start rotating. So 1, 2, 3, 3, 1, 0, then 0, minus 1, 1, see 0, minus 1, 1, then 1, 0, 1. So this is a 90-degree rotation of this particular 2D matrix. And the center element doesn't move, it stays the same. Okay, now what do I have to do? Rotate it again by 90 degrees more. So that's easy. So what will happen to this 1, 0, 1? It will appear over here. Then 1, 2, 3, then 3, 1, 0, then 0, minus 1, 1. So this is the rotated kernel by 180 degrees. Okay, now we'll do the convolution, which is extremely easy. What we'll do is we'll place the center pixel stays in the center position. So now you'll place this kernel right over here in the first 3 by 3 spot. Okay, remember in the continuous domain, convolution is multiply and integrate. In the discrete domain, it is multiply and add. Okay, multiply and sum. So now all you have to do is multiply the position over here and add. So what will be the answer? 95 times 0, 0. So then, 0 times 95 plus negative 1 times 91 plus 112 times 1 plus 83 times 1 plus 70 times 1 plus 0 times 40 plus 91 times 3 plus 82 times 2 plus 65 times 1. Okay, this goes 0 out, negative 91, 112 will become 21 over here.
676.
Is it 676?
Yeah.
Okay, so that will be the answer after we do the convolution with this kernel, with this one. And so the answer that it will produce will be right over here, 676. Because remember, the kernel was, so whatever is the center position of the kernel, that's where the data is produced. Okay. Now you might be wondering for images in grayscale, what's the range of pixel values? 0 to 255. So 676 doesn't make any sense. Okay. So when we create kernels, what we do is we make sure that once we do the convolution, it will not scale up or scale down, meaning the sum of all these values in a proper image processing kernel has to be 1. It cannot exceed 1. So if I add up all these values, what's 1 plus 2, 3 and 3, 6 and 2, 8 and 1, 9 and minus 1, 8. So to make it a proper kernel, I have to divide it by 8. Okay, so the actual answer of the convolution will be 676 divided by
84.5.
So 84.5, and that's the first value we will produce. Okay. Very similarly, after we produce one answer, just like as we discussed in convolution, we keep sliding. So now we'll slide the window to this position. Oops. So now slide the position to this window, right? And we'll produce an answer now in this spot.